We built the most powerful and versatile femtosecond lasers with a clear focus on next generation EUV technology. And that's what actually this conference is all about. Our few cycle optical parametric chirp pulse amplifier at 2 micron wavelengths with up to 100 watt of average power. This work is a cooperation with the Advanced Research Center for Nanolithography in Amsterdam with a group of Peter Kraus. So I will first give a little introduction motivating those types of lasers and XUV sources for modern EUV chip making. I will present important technical details of the laser system and finally conclude with a specific beamline design and an application example in ultrafast spectroscopy and its scalability to the soft X-ray regime. So the motivation behind our work becomes clear when we take a look towards modern and future chip making, which is enabled by EUV lithography at 13.5 nanometer wavelengths and even beyond. The current wavelengths of 13.5 nanometers is about 14 times shorter than the currently used DUV process and allows a much higher density of transistors. I mean, the previous talk gave a little insight on that. So the nanometer scale patterns of transistors or of features on this semiconductor wafer here is being produced by exposing a negative photoresist layer on top of the semiconductor with the EUV light. The further development of such photoresist chemicals is a continuing challenge that targets, for example, the improvement of the photosensitivity. So the question is, how can I make my photoresist more sensitive, and hence how can I make the whole process even faster? Now, the group of Peter Kraus at ARCNL develops and utilizes novel HHG-based methods to investigate ultra-fast and ultra-small processes that are related to modern chip making. One interesting example is exactly that photoresist question from my previous slide. So let's have a look on that. What we see here is a schematic of a modern EUV photoresist material, a so-called tin oxocage. So we see a compound of hydrogen, oxygen, and tin embedded in OH groups and then stabilized by these butyl side chains, which look like little hairs. So one could see in high harmonics-based absorption spectra that those bonds here between the carbon in the butyl chains and the tin are stripped off upon UV exposure. So those type of measurements show basically a before and after image, and by removing the side chains, it looks like the whole compound undergoes polymerization, and thus we get this chemical contrast that we need in order to create features in this photoresist. But now, having this before and after picture, the exciting question remains, what are the exact electronic and molecular processes involved, and how can we, based on that knowledge, engineer a more efficient photoresist? Here, a technique called soft X-ray transient absorption spectroscopy comes into play. So yeah, as I said, the side chains here contain carbon, and we want to be able to pump this photoresist to trigger the chemical reaction, and then probe specific points in time with a broadband attosecond pulse that is ideally in the water window, covering the carbon kH here at 285 eV and the oxygen kH at 534 eV. For this purpose and other purposes, the HHG and EUV science group at ARCNL develops a new soft X-ray source with the goal to provide brilliant water window attosecond pulses here at a repetition rate of 50 kilohertz. So we provide this overview that shows the average power of a number of HHG sources that have been published so far versus photon energy. And here in the water window region, between 285 and about 600 eV, we see clearly that 1 kilohertz systems dominate. And this is because we need really millijoule class driver lasers in longer wavelengths, such as 1.5, 1.8, 2 micron, in order to nicely cover this spectral window here, this important spectral window. And now for the first time, we are going to use a millijoule level few cycle laser system with 50 kilohertz repetition rate to realize such a source. Now, our solution at Class 5 Photonics is a mid-infrared optical parametric chirp pulse amplifier. Looking at those systems, we have another overview that shows pulse energy and repetition rate here in a double logarithmic scale. And you can see where the challenges set in. Here, those diagonal lines show the average power, which is the product of the rep rate and the pulse energy. And now when we want to reach the millijoule range, we see that at 50 to 100 kilohertz, we easily reach the 100 watt average power regime. So such systems require a delicate interplay of kilowatt class ytterbium lasers as pump sources, high power nonlinear optics, advanced dispersion management, and thermal design. So at Class 5, we have already successfully demonstrated 100 watt average power OPCPA at 1.8 micron at SLAC. We could operate the system also at 2 micron with 65 watts. And now I would like to take you on a little journey of our development of the few cycle 2 micron system that is currently operating at 50 watts. This is how it looks like. This is the key principle. Basically, we have a pump laser, which is a kilowatt class ytterbium YAG picosecond laser, usually an InnoSlab or a thin disk laser. And in this schematic, we show an Amphos InnoSlab that consists of 3 modules. We have a 400 watt preamplifier, we have a kilowatt main amplifier, and then we have a high power compressor that compresses the pulses down to about 1.5 picoseconds to seed our commercial OPCPA here. That is shown nicely in the front. And I would like to have a more detailed look now on what is in the OPCPA. So again, the goal is to get few cycle pulses at 2 micron. So we use this kilowatt pump laser at 50 kilohertz. It has a pulse energy of 16 millijoules here after the main compressor. And there's a little auxiliary compressor, which gets a little bit more bandwidth, and we can get slightly below a picosecond. And this is being used to drive actually the seeder. So in order to build a 2 micron system, we need, first of all, a CP stable broadband seed. And that's realized here by white light generation and subsequent difference frequency generation. So we get a nice spectrum ranging from 1.8 to 2.4 micron that corresponds even to sub 20 femtoseconds Fourier limit, which is quite nice. So now we need to further amplify those pulses in our first preamplifier OPCPA stage, OPCPA.min. And here we have 2 main challenges. One is the dispersion management. So we have to stretch the pulse from about picoseconds to 1.5 picoseconds. We do this by bulk silicon. And then secondly, we need to compensate for the timing drift that occurs between this low power output and this high power output here. We do that by implementing cross correlator and then feedback the system to get femtosecond level synchronization. And by doing that, we can ensure a stable output of this preamp. So you see 14 hours of operation with 24 microjoules here. Also a nice symmetric beam profile. Now, this output has to be further amplified now to the final power. And now the challenge is really that we have to operate this crystal under an average power of 800 watts and an intensity that approaches the 100 gigawatts per square centimeter that is required. And that really puts quite some constraints, not only by the thermal effects in those crystals and on the optics, but also by the nonlinearities due to the high pulse energy and the short pulses. So all optical coating materials and substrates need to be selected according to those criteria. And in the current configuration, we have successfully achieved about 1 millijoule broadband pulses at 2 micron central wavelengths using these 16 millijoules as a pump. The conversion efficiency is slightly above 6%, but in the moment mainly limited by the mentioned constraints like the thermal effects and the nonlinearities. But we are targeting a factor of 2 in gain to get towards 1.6 millijoules by implementing a third OPCPA stage here. So the compression is designed for a chirp mirror array with a negative GDD and TOD compensation. Currently, we achieve 41 femtosecond pulse duration using a preliminary compressor that is just made of bulk fused silica, which has a negative GDD. But of course, uncompensated third-order dispersion is clearly visible here in this frog retrieval. And with the final chirp mirror design, we expect high fidelity pulses that are sent at around 2 micron wavelengths with at least 35 femtosecond pulse duration. But we are targeting much shorter pulses here, as you can see also for the bandwidth that we can amplify. Such passive dispersion design has been proven already in our 800 nanometers and 1.5 micron systems. And yeah, we see this in the millijoule range being an ideal driver for water window high harmonic generation. Now, in the last part of my talk, I would like to give you an outlook on the facility itself. So the beam is the laser is being implemented now in January to ARCNL, and we will have a high harmonic generation, a high pressure gas jet here, an infrared removal section to filter out the 2 micron, and then a toroidal refocusing mirror that focuses the focus of the target here to the sample interaction chamber. After recombination with the 2 micron, the interaction chamber can be used for coherent diffractive imaging experiments with an in-vacuum camera and also for the transient absorption spectroscopy. And now, finally, I would like to have a closer look into this chamber, into this experiment. So the transient spectroscopy instrument itself will have a solid target in reflective or transmitted geometry. So usually it's reflective. And such type of experiment has been demonstrated by the group of Peter Krauss using germanium and the 1 kHz system. So in that case, they used a few cycle visible IR pump pulse for exciting carriers across the band gap and monitor the induced dynamics by reflecting a second pulse, which is in this case an XUV attosecond pulse. So in order to understand those measurements, we can have a look to a simplified energy diagram here. First, the visible pulse excites electrons here from the highest occupied molecular orbit, which corresponds to the valence band, to the lowest unoccupied molecular orbit, which corresponds to the conduction band. And now this increases the hole density here and the electron density here that induces a shift of the band gap. Now, this shift can be probed using a broadband EUV pulse, which is this one, or let's keep in this little plot here. This can be now probed with an EUV pulse between 28 and 32 eV, which excites the 3D core electrons from the germanium M edge into both of those bands. Now, this leads to an increased absorption here in the valence band and in a decreased absorption in the conduction band. And actually, this is what you can see here. At point 0, we can see the increased absorption here in the valence band and the decreased absorption here in the conduction band. We also see that the band gap has shifted and increased. And now with the pump probe technique, we can trace now this band gap relaxation, and such reflective measurements on the ultrafast timescale give us direct access to the dielectric function and thus to the chemistry happening on that timescale. So now we are now planning to do this in the water window and on the photoresists finally. So yeah, for this purpose, there's going to be a 50 kilohertz source at ARCNL, and class 5 delivers a mid-IR millijoule level few cycle OPCPA at 50 kilohertz. I would like to thank you for your attention, and if you are interested in learning more, then follow us on our channels or send us an email. Thank you.